especially if we expose this sample to ultraviolet light. We can see it glow. There are three different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation. Here we have a nuclear scaler that measures...
Now, alpha, beta, and gamma, right? He called them all radiation, and they all are radiation. Well, let's go here just a second. Now, is this a particle or pure radiation? No, this is a particle. Okay, alpha particles are what? A nucleus of which atom? Helium. Okay, good. Now let's go to the beta. Whoops, passed them by. There we go. Beta. What is that? Does it have any mass at all?
Yeah.
Yeah, 1/11800th of an AMU. Very, very small. So for all intent and purposes, this guy has no mass, but he is a particle. Now when we get over here to gamma, that gamma dude is no mass at all. It is pure radiation. And this is the dangerous guy. This guy is dangerous because he can go through anything, as you're going to see in this video.
Here we have a nuclear scaler that measures...
What's a name for the nuclear scalar? Starts with a G. A something counter. Starts with a G. Geiger counter. Geiger counter. Okay, here we go.
Radioactive decay.
Now, I want you to watch this guy right here. Okay, watch how fast he's going, and then we're going to compare it before and after he puts the radioactive source in. Here we go.
Click that you hear is a nucleus of an atom that is decaying by
giving off a radioactive particle. See how fast he's going around? Pretty slow, huh?
This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler.
Watch that again.
What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection.
So when you think penetration, it's how easily does it go through? Okay? How easily does it go through?
Let's place a beta particle in our sample.
He meant to say beta particle source. Okay, this is a source for beta particles.
We notice that there's a slight increase
See it?
in the
See how fast that's going around?
The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. We notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample.
What's your prediction? Okay, now I want you to think for a minute. What did I just tell you about gamma radiation? Goes through anything. So, when we put lead over the gamma radiation source, what is that going to do to the count? It's practically nothing? Really? Okay, well, let's see.
Oh.
Listen to that guy go, huh?
Immediately that more energy comes from the gamma. 1 sheet of lead and 2 and even 3 that...
Do you hear any difference? Not really.
Quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles, alpha and beta. Gamma is an electromagnetic energy wave. Well, let's see what happens as we go from being close to a radioactive source to far away.
Okay, now, what is your prediction? Okay, how many think it's going to be nothing? No change? A lot of you said nothing. Okay, how many think it's going to go down some? And some of you don't think at all. Okay. Big difference,
We
huh?
notice that the amount of radioactivity is greatly decreased by distance.
That's why with CRTs, which are what we have in this television up here, this television has a cathode ray tube in it. We were advised very early in the production of televisions not to watch too closely to the tube. Why? Because there was radiation coming off of it from the electrons, which are beta particles, right? Electrons being shot off of the tube. It goes right through the glass. Okay, so you don't want to be having your eyes irradiated with beta particles. That's not good for your eyes. And that's why they told you not to do that. So you put a little distance between you and the television, like 5 to 10 feet, you're not getting any appreciable radiation. So that's why we did that. And there we go. Okay, now let's take a look at what we're going to need to know to be able to do our worksheet. I would like you to take notes on this. I'll show you the whole thing. Okay, I actually did some magnification of this line down here, and I want you to take some notes on this using this video if you're watching at home, or just copying what I've got in front of you here if you're sitting in the class with me. What about this blue line stuff here? What does that mean for these two guys? They are, okay, and here the gamma radiation. Not a particle, very high energy radiation. So in this part right here, we're actually talking about size of particles and bigger going to the left. Notice here that the helium nucleus has 2 protons, 2 neutrons, but it has a charge of 2 positive because there are no electrons. And then notice again that the most dangerous to people is the gamma ray. Why? Because it'll go through anything, and when it gets to your DNA, it will damage the DNA, which we say is changing the DNA, which it does, because it could damage any part or all of a DNA molecule, depending on how much hit that molecule. Yes, question? This business of the positron, of course, is very weird because we just don't normally see that kind of thing. We think of an electron as always being negative, and in nuclear reactions, we have that strange thing as well as other things that get kind of strange. This little chart is in your textbook, and you might notice the mass of a beta particle really, really small, and literally for a gamma particle there is no mass, which is why you see the 0, 0 for the mass number and for what we used to call the atomic number if we're talking about a normal atom. But these guys are different kind of stuff. So this doesn't really mean it's a negative proton. It's just a charge, okay? And we'll see how that comes to play in the nuclear equations because they balance really, really differently. Now let's get a feel. This guy is on page 106 of your textbook at home, and let's make sure we understand what we're looking at here. Here's a positive plate. Here's a negative plate, and I don't mean a plate like you eat off of. I mean a metal plate that's hooked up to an electromagnet. Okay? So, as we look at what happens, why would the beta particle swing upwards? Okay, it's a negative charge, so it's attracted to the positive plate, and it's also pushed away by the negative plate, right? Now, here's the alpha particle. Why does it go down? Okay, because it's a positive charge, it goes the opposite direction. So we can separate beta and alpha particles this way, if we have a continuous stream of particles. And then, why doesn't this guy go up or down? No charge at all. Okay, so magnetic fields can't affect it at all. Okay? Now, this is a little tutorial on the difference between balancing a chemical equation and a nuclear equation. So let me just close up here and cover the top part, and let's talk about chemical equation first. Yeah, absolutely. You want this. You really want this. Now, this won't help you for tonight's homework, but I think most of you had the opportunity to do balancing of chemical equations. Haven't you done that? Didn't you do that in 8th grade? Yeah. Okay. So you may be aware that all we need to do to balance this is to put 2's here and here. But what are we doing? We want same number of what on both sides? Particles. Same what on both sides? Atoms. Okay. Same number of atoms of each kind on both sides. So that's what it's all about. If you look on the left side, you're going to have 2 times 2 hydrogens, which is 4. 2 times 2 hydrogens here is 4. 2 oxygens here because of the subscript, and 2 oxygens here because of the 2 coefficient. So what we're accomplishing is what I wrote in green there. Now, contrast that to a nuclear equation, and we got to worry about all these guys. Okay? We balance our equation by using these. And we can figure out things that are missing in a nuclear equation by knowing what they are. So a neutron is got a mass number of 1, but no charge. A proton has a mass number of 1 and a charge of 1 plus. Okay, so I've added the positive charge in. So for a proton, we have a 1 mass number and a 1 plus charge. Electrons, or the normal beta particle, is a 0 mass, essentially, not really 0, but a 0 mass, and a 1 plus charge. Oops, I got these guys backwards. I are. Get that fixed. Ouch. That's terrible. R. Swap these guys out. And as long as I'm doing the swapping, I like the smaller plus, so I'm going to grab that. Copy and paste. Here. Get rid of him, and there we go. Okay, so everybody got this down? Here we go. Now, let's look at the first and most simple one, which is beta decay. In beta decay, we are looking at a carbon-14 atom changing to a nitrogen-14 atom. That's kind of weird, huh? What did change? What changed between these? Now, wait a second. The mass number didn't change. So, where'd the extra proton come from? Ah, not sure, are you? Okay, we had a turncoat. One of the neutrons in the carbon changed to a proton. Weird, huh? And in order to do that, it had to discharge an electron. That's the first take on it. The second take on it is, now, how do we balance this guy? Watch and learn. 14, the number on the top, has to be equal on both sides of the arrow. 14 equals 14 plus 0. On the bottom, we have to balance. 6 is equal to 7 minus 1. Ah, pretty cool, huh? It is balanced right. Now, here's what you're going to be doing in your little worksheet. Let's say you don't know what the other guy is. What you do know is that you have carbon 14 to start, and you have an electron being given off, or a beta particle. Here's what we do. I don't know what the element is, so I'm not going to put in its symbol. But what does the number under the black square have to be to make the atomic numbers the same, or balance, I'm sorry? Has to be a 7. Okay, and what's the number on top have to be to balance on both sides?
14.
Yes, 14. Sorry, I spaced out there a minute. All right, now we look on the periodic chart. Who's element number 7? That's where we get our symbol. Nice, huh? That's how it works. Okay, and as we see, that's what's under there. Okay, now, here, before you have a chance to look, let's try it with this guy. Okay, another beta particle expulsion. So, the number in here has to be what on the top? See? Because this is a 0 and this is 134, that means the number in the black on the top has to be 234. And on the bottom, we have 90, and this has to be 91 because of the minus. Okay, so 91 minus 1 is, and this is protactinium. Looks like the abbreviation for Pennsylvania. Okay? That's the kind of thing you're going to be asked to do on your worksheet. Okay, now let's look for alpha particles, and let's take our little box down and work our magic with the alpha particles. Sometimes you'll be asked to find that guy. Okay, now here's the new element. We changed from thorium to radium. Okay, so this guy's 90, this guy's 88. What does our new guy in the middle have to be? Huh? 2. Sure, he has to be a massive, or atomic number of 2. What's the number going to be on the top? 4. And who does that describe? Who's element number 2? Helium. And this is who? What do we call that particle? Making sense? Huh? That's how you work this stuff. Here we go. Let's do a couple more here. Let's figure out this guy. Here we go. We're starting with iodine. Okay, so we've got iodine over here on the left. We've got a beta particle being given off, beta decay, right? And so we got to figure out this box. So, what's the number on the bottom have to be? We got 53 is equal to minus 1 and what? 54. So that gives us the symbol. Who is it? 54. Xenon. Aha! A xenon. And what's the number on the top have to be? 131, right? Because we have the beta particle with a 0 mass number. Okay, let's go down here, and let's figure out who is the mystery guest on the right. So what's the number on the top have to be? For our mystery guest, we've got 22 here, 22 here. This number has to be a what? Yes, indeed. So this guy's a 0. What's the number on the bottom have to be? 1 what? Ah, it has to be. And who do we call that guy? He is a what? He is a positron. Okay? Positron. That's how we write him in the equation. Okay? Now, production of an alpha particle. Let's go down there. See how this guy works. Ooh, yeah. Okay. So, let's check him out. Uranium. What's uranium going to change to? So, we've got 92 here. We got here. Oh my, go back. Okay, let's use this arrow. We got 92 down here, 2 here. So over here we had to have a 0. And what's the number inside the box? 90. Now as we figure the top number, we have to realize that we have a 0 here, and a 0 here, and a 4 here, I'm sorry, and we got 238. So what does that number in the middle have to be? And of course, it has to be 234. Now, the 90 is what, and let's write the 234 over here. This 90 down here on the other particle tells us that the atomic number for our mystery guest over here is, as we look up on the periodic chart, number 90 is thorium. Okay? So that's going to be a TH. And just in case you're not finding it when you look on the chart, look down below the chart in the very bottom line that goes across, and you'll see that on the far left. That's where thorium is. So let's go ahead and do the last ones. Oops, that is the last one. So I hope you find this helpful. And here's a little chart that is on page 586 in the Zumdahl text. And this is kind of a summary. You may wish to have this as a reference. Very, very, very nice reference chart. And that's it, folks. I hope you find this very helpful.